Okay, section 10.3 begins on page 698. And so when we talk about probability, we're basically talking about the chances of something occurring. And there are a couple of different kinds of probability that we're going to talk about. There is theoretical probability, there's experimental probability, there is also geometric probability. And then within things like theoretical probability, there are different types of probability in there as well. So we're going to talk about theoretical probability right now. And probability in general, guys, is going to either be given as a percentage or a fraction, or it can be listed as a decimal between 0 and 1. So as a percent, it's between 0 and 100%. As a fraction, it's between 0 and 1. As a decimal, it's between 0 and 1. So all of these represent something between 0 and 1, or 0% and 100%. 0% means there's no chance that the thing can happen. Not that it's unlikely, but that it's actually impossible for it to happen. 1 means it's an absolute certainty that it's going to happen. There's no way for it to not happen. That's the idea. All right. So theoretical probability is a measure of what we would expect from a particular experiment. And so when we talk about probability, we talk about the probability of some event. And the way we write it is like this: P of something happening. Okay? Flipping a coin and getting a heads. Rolling a die, a six-sided die, and getting a 4. The probability of an event happening is equal to a fraction. And that fraction in the numerator has the number of possible successes. In other words, how many different ways can this event actually occur? How many ways can you flip a coin and get a heads? How many ways can you roll a six-sided die and get a 4 or get an even number? Things like that. Divided by the number of possible outcomes. So total possible outcomes. Now, this is not the same thing as odds, although it's related to odds. We'll talk about odds in a few minutes. So the number of possible successes divided by the number of total possible outcomes. Because these are numbers, because we need to count these things up, we need to know how to count very accurately, especially in complex situations. And that's why we learned about factorial, and that's why we learned about the counting principle, fundamental counting principle. That's why we learned about permutations and combinations. These are all tools that help us count so that we can get that numerator and denominator correctly. So for example, if we want to throw a fair coin, two-sided coin, and we want to know what's the probability of getting a heads, how many different heads are there on a coin? 1. How many different outcomes are there on a coin? 2, right? There's only one heads, there's a heads, and there's a tails, right? So the probability of throwing a fair two-sided coin and getting a heads is 1 out of 2, or 50%, or 0.5. Okay, it can be written as any of these. Typically, we're going to stick with this, unless it tells us otherwise. Okay? But any of those are acceptable. Questions about that? Okay, what about the probability of rolling a six-sided die, a fair six-sided die, and getting a 4? The singular of dice is die. So how many 4s are there on a 6-sided die? 1. So 4. How many possible outcomes are there? 6. 1, 2, 3, 4, 5, or 6. So the probability is 1 over 6. Okay? What if we rolled the same 6-sided die and we wanted to get an even number? How many even numbers are there on a 6-sided die? 3. 2, 4, and 6 out of how many possible outcomes? 6. 1, 2, 3, 4, 5, 6. That reduces down to 1 over 2. We're back to 50%. What if we wanted to throw a 6-sided die and we wanted to get the probability of a number less than 3? Now how many successes are there? 2. 1 and 2, right? How many outcomes? 6. 1 through 6. And so that would reduce down to 1 over 3. Now, you guys don't have to write this stuff. I'm writing it just so you can see where we're getting those numbers from. You can write it if you want to, but you don't need to. That's just for illustration purposes. Okay, questions about that? That's the gist of probability, guys. Now, obviously, probability seems very easy, but it's not always quite so easy because, as we've seen, counting is not always quite so easy. All right. So let's take a look at, I already did those. Let's look at example number 2. So example 2 in the book says the following. The community center hosts a talent contest for local musicians. On a given evening, 7 musicians are scheduled to perform. The order in which the musicians perform is randomly selected during the show. What is the probability that the musicians perform in alphabetical order by their last names? Assume that no 2 musicians have the same last name. Okay. Well, we have 7 musicians. Okay? So, let's think about this for just a moment, guys. If there are 7 musicians, how many different orders can those musicians come up and perform? Well, we have the first position, second position, third, fourth, fifth, sixth, and seventh. How many choices for the first one? And then that's our 7 factorial, right? Isn't that the same idea as if we have a word, how many different orders can we put the letters in that word if there are no duplicates? And they told us there are no 2 last names that are the same. Do you see it's the same idea? Okay, as having a word where we're going to rearrange the letters with no 2 letters alike. So, this is the total outcomes. So the probability that they go in alphabetical order, the total number of possible outcomes is 7 factorial. I like to actually start with that number first, the one on the bottom. The total number of possible outcomes. The question is, of all those different orders, how many of them are alphabetical from first to last? 1. There's only 1 correct alphabetical order. So how many possible successes? 1. And so the probability then is going to be 1 over 7 factorial. So 1 over 5,040, or if we wanted to actually get this as a decimal, you don't have to unless they ask you to. I would just leave it as a fraction. But just to give you an idea, it's 1.98 times 10 to the negative 4th power, right? So just to give you an idea, that's 0.000198. So if you make this into a percentage, you move that over 2 times, it's 0.0198%. So it's less than 2/100ths of a percent chance that if you just randomly pick among 7 people with different last names that you're going to actually pick alphabetical order. Pretty tiny, right? Okay, questions about how that works? Now let's look at part B. Part B says you are friends with 4 of the musicians. What is the probability that the first 2 performers are your friends? So again, Now we're only going to look at the first two performers. So now it's not 7 factorial. Now we're just looking at these first two spots. So the probability that the first two are your friends. So how many performers are we looking at? 7, right? Now, we're going to put them in order. For this particular, for the last problem, did order matter? Yeah, because we were looking at the order based on last name, right? So order absolutely mattered, right? Brown and then Charles was not the same as Charles and then Brown, right? It's a different outcome. But for this, since all we care about is whether or not they're our friend, it has nothing to do with any particular order, does order matter now? No. So now we're going to use combinations. And so for the total number of outcomes, we have 7 musicians to choose from. We're picking how many places? We're only picking 2 places this time, right? Because we're only looking at the first 2. Because we just want to know the probability that the first 2 are one of our 4 friends, or 2 of our 4 friends. Make sense, everybody? So do you see how you have to read the question carefully? Right? You have to identify how you're going to count. In this case, we're going to count using combinations, not factorial. Now, the question is, what goes on the top? How many successes? Well, how many of our friends do we have to choose from? 4. And how many are we going to choose at a time? 2. This is going to give you your probability. The 4 choose 2 tells you how many different outcomes include 2 of your friends. But order doesn't matter. So it doesn't matter if you pick Fred and then Barney or Barney and then Fred, right? Okay. Everybody get that Flintstones reference? Just making sure. So this ends up being 4 choose 2 divided by 7 choose 2. We get 6 over 21, which reduces down, and you always reduce fractions, guys. This reduces down to 2 over 7. Okay, 2 over 7 is about 28%. So about 28.6%. So there is a good chance that the first 2 are 2 of your friends, because 4 out of the 7, more than half of them are your friends, right? All right, questions about that? So do you guys get the gist of how probability works? Now again, this is theoretical probability. Now we're going to talk about experimental probability. Experimental probability is now we're not going to just sit there and think in our heads, okay, how many different possible outcomes are there? How many different possible successes are there? Now we're going to actually perform the experiment. We're actually going to flip the coin over and over and over. We're actually going to toss the die over and over and over. Now, before I talk about experimental probability, going back to theoretical probability, guys, what this tells us is that, for example, if we flip a coin over and over and over, we expect about 50% to end up being heads. Does that mean every time I perform this experiment, we're going to get half heads and half tails? But if I flip a coin twice, am I going to get one of each necessarily? No, that's not what probability means. Probability means that if you do this not once, not 10 times, not 100 times, not 1,000, not 1,000,000, but if you do this over and over and over repeatedly, the total outcomes, successes over possible trials, should approach 50%. It should zero in on 50%, not in the short run, but in the long run. In the short run, anything can happen. Can you flip a coin 100 times and get 100 tails in a row? Absolutely. Okay? When you go to, if you got 100 tails in a row, when you flip that 101st coin, or you flip that same coin the 101st time, what's the chances of getting another tails? It's still 50-50, right? Okay, so the probability for any particular outcome is 50-50 there with a coin, 1/2. But again, we don't know what's going to happen in the short run. We only know that in the long run, we would make the prediction that we would get 50% heads and 50% tails. Does everybody understand that? We would expect in the long run that 1 out of every 6 times we throw a 6-sided die, we get a 4. Or 2 out of every 6 times, 1 out of every 3 times we throw it, we're going to get a number less than 3. That doesn't mean that if I throw it 3 times, I'm going to get one number less than 3. Okay? Let's do a quick experiment on that one. We got a few minutes left. Okay, chuck them at the screen. Thank you. Okay, so if we're looking at the probability of a number less than 3, we got a 3, a 5, and a 5. How many of those 3 were less than 3? None of them. So we actually got 0 out of 3, not 1 out of 3. But we would expect that if we did this 1,000, 100,000, 1,000,000 times, we would see that that probability would approach 1/3 of the time. It would get closer and closer and closer. And the more times we did it, the closer it would eventually get to 1/3. That's the idea of probability. There's no guarantees. It's just what we would expect theoretically. Does everybody get that? So now when we talk about experimental probability, now we're going to do what we just did. Experimental probability of some event is not the number of possible successes divided by the number of total possible outcomes. It's the number of actual successes divided by the number of trials. In other words, how many times did we perform the experiment? How many times did we throw a 6-sided die? How many times did we toss the coin? That's the bottom number. What goes on top? How many actual successes you got. So for our quick little experiment where we threw the dice and we got a 3, a 5, and a 5, if we wanted the probability of getting a number less than 3, how many trials did we perform? How many dice did we throw? 3. So we threw a 6-sided die 3 times. How many successes did we get? 0. So our experimental probability was not 1 out of 3. Our experimental probability was 0 out of 3. Now, does that mean there's no chance of it ever happening? No. It means that we didn't see it happen in our experiment. Now, notice we had what's called a very small sample size. Would you want to make any predictions? Would you want to bet any money based on the outcome of just 3 trials? Yeah? So you're willing to bet what's going to come on the next throw? You like to take a risk. Well, that's the idea, is understand that that's taking a risk. Right? It's not enough information for you to make a reasonable prediction. Right? It would be a total guess, a total risk, right? Now, that's when you start to look at risk and reward. If you're playing a game that costs money, right? If you win $10, if you're right on the next guess, whether it's going to be less than 3 or not, right? But it costs you $5 to play, you'd have to make a decision if that game was worth the risk. If the cost, right, was worth the risk. Or the reward, I should say, was worth the risk. Okay. Questions about that, guys? So that's experimental probability. So if you flip a coin 1,000 times, and you get 300 heads, that reduces down to 3 over 10. That's 30%. That's actually a little bit on the low side, right? Actually quite a bit on the low side, because we would have expected that number to be closer to what? 50%. But our experiment shows us 30%. So we would expect that if we did it another 1,000 times, maybe we would get more than 50% and it would start to average out to closer and closer to 50%. So does everybody understand the difference between theoretical probability and experimental? Okay. I now want to talk to you guys about odds very quickly. This is a question that came up the other day. Also, remind me, I see you guys tomorrow, right? Remind me tomorrow about the issue we had with that probability problem, because I figured out what we were double counting. So if you remind me about it tomorrow, I'll talk about it. Okay, odds. The odds of some event happening are similar to probability, but not the same. Probability is the number of possible successes over the total number of possible outcomes. Odds is the number of successes divided by, or possible successes, divided by the number of possible failures. Now, if you know one, you know the other, but they're not the same measure. So, for example, if we want to know the probability of getting a 4 on a 6-sided die, we said that probability is what? Sorry, guys, I need to restart this. Bear with me a second. Let's see if that works better. Okay, so the probability of getting a 4 on a 6-sided die, there's 1 4 out of how many possibilities? 6. The odds of getting a 4, how many possible successes are there? 1. How many possible failures are there? 5. So here it's 1, here it's 1, 2, 3, 4, 5, and 6, just so you can see it. Here it's 4, excuse me. 4 is our success. 1, 2, 3, 5, and 6 are our failures. So this is the difference between probability and odds. Probability is successes over outcomes. Odds is successes over failures. Okay? Do you see how to get this number 6 from the odds? Probability is number of possible successes over the number of possible outcomes. This number of possible outcomes is really successes plus failures. Right? Isn't that the total number of outcomes? All of your successes plus all of your possible failures? So if the number of successes is 1, the number of failures is 5, how many total possible outcomes are there? 6, right? So that's how we get the 6. Likewise, if you have 1 success out of 6 possibilities, then how many of those 6 possibilities must be failures? If there's only 1 success. 5. So again, if you know one, you automatically know the other, but they are not the same. Now, this is odds in favor of an event. Now, when you look at odds like in sports betting, in the newspaper, things like that, it's never something like 1 to 5 or 2 to 7. What does it always look like? It's like 5 to 1, because they're not giving you the odds of success or in favor, they're giving you the odds against. So odds against an event. And here's where you just have to ask yourself, guys. Again, it's going to be the number of successes divided by the number of failures, right? By that definition up there. But if you want the odds against an event, that means you want the event to not happen, right? So do you guys see that that means that the success would be the event not happening? Does that make sense? So it would be, in essence, the number of failures of the event divided by the number of successes. And so odds against would be 5 to 1. So in horse racing, you see this all the time. In sports betting in general, you see this all the time. Okay? If you go to Vegas and you want to see the odds of the San Diego Chargers winning the Super Bowl, it'll be like, you know, I don't know, 35 to 1 or something. I don't know what it currently is, but that's the idea. It's not going to be 1 to 35. It's going to be 35 to 1. They're going to give you the odds against.
So is it number of possible scenarios?
Possible, because this is back to theoretical. Yes, this is theoretical. Let's see. Questions about any of that? All right, guys, we're just about out of time. I want to give you the assignment. We haven't talked about everything in here, so I do want you guys to go through and read the section on your own and look at the other examples. But I want to give you the assignment to work on tonight, and we will clean up any issues tomorrow, and then we'll start to talk about some of the types of theoretical probability.